Okay, so let's do some gradient descent. We first create an optimization object, and I'm gonna use this SGD class, which implements stochastic gradient descent. We're using it basically as the gradient descent algorithm. We pass it a list of variables that we want to optimize. In this case, it's just a single variable. And then we pass it a learning rate, which is basically the step size of the gradient descent. So what this is supposed to do is when we take a step of the gradient descent, we would like to calculate negative the step size times the gradient, which is stored in w.grad, and add it to w. So we want to calculate this. So if I maybe run these, so the first or the initial vector is w, and then this is negative the step size times the gradient, and we get, when we add them up, we get this. So we expect the first step of the gradient descent to move us from this point to this point. Okay, so how do we do this? So what you can do is that you can call the step function on the, or step method on the optimization object. So we do it a couple of times, so let me run this. So at first I print the tensor and I also print the loss. And you can see that that's our initial vector. And after the first step, I'm printing the tensor again. So you can see that the first step is as we expect. The subsequent steps are not correct, however. They're not doing gradient descent. And the reason is that this optimization step, it just moves w. So it doesn't update the gradient. So we keep adding the same gradient or scaled gradient to w. So you can verify, for example, that this is just adding negative 0.1 times the gradient of w to the previous step. And this is obtained by adding the same vector to the previous step. In mathematical notation, what this is doing is calculating this, or performing this update. So you add the gradient at the initial vector times the step size, or a negative of this, to w at time I, to get w at time I plus 1. So this is not a gradient descent. Also note that I'm printing the loss, and the loss is not changing either. So this optim.step really just updates the w. It doesn't change the loss, it doesn't change the gradient. And just one note, when you apply the item function on a tensor that has a single element, it just outputs that number. Okay, we're using that, and this is the description from the documentation. Okay, so let's try to correct that. But first, let's improve the code a little bit. Here I'm defining a function that computes the loss, and it takes a dummy variable u that calculates the loss that we had. So now if I create the w tensor as before, and I apply this function to w, I will create the loss. One thing that I want to point out is that when doing this, the loss still keeps track of w, so it has a reference to w. Because when I pass w to this function, although I'm using u here to create the loss, in Python u would be just a reference to w. So what I'm doing really is equivalent to doing this operation, more or less. So when I do this, the loss gets a reference to w, and when I call loss backward, this will update the gradient of w. As you can see here, so the output is the same as before. Okay, so this is attempt 2 at creating or performing gradient descent. So I have my initial vector, and I have my optimization object, and I'm doing this loop. So first I compute the loss based on the current value of W, then I perform this backward operation, which updates the gradient, changes W.grad, and I'm printing the gradient, and then do optimization step, which just changes W. And so this looks like doing the gradient descent, because every time I change W, the next step I update the loss, and I also update the gradient. And so the next step will be based on the updated gradient. Okay, so let's run this. So the first, in the first step, the gradient is as before. The first step of the gradient descent is correct as before. But if you check the subsequent steps, there is something wrong still. So you can see the gradient is growing, and we know that the first element of the gradient has to be 5, for example. You can see it goes to 10 and 15. So what really happens is that we are changing the gradient. It's not obvious, but the gradient is changing, but it's added to the previous value. So we're accumulating the gradient. Mathematically, what this is doing is doing this update. So instead of subtracting the gradient at the current value, we're subtracting the sum of all the gradients up to the current time. And this is not gradient descent either. Okay, in order to perform the correct gradient descent, we just need to zero out the gradient every time we want to update it. Before updating it, we want to zero it out, and this is easily performed by this optim.zeroGrad function. So this is the only addition to the previous block of code. So at the start of the loop, we zero out the gradient, we compute the loss, we update the gradient, updates W.grad basically, and then we update W. So each operation modifies a certain tensor. So this modifies W.grad, this updates the loss, this modifies W.grad, and this modifies W. So if I run this, you can see that the gradient is moving. That's my initial gradient. This is the second step gradient, and this is the subsequent gradient. And the first coordinate is correct, and we can actually verify shortly that this is actually the correct sequence of gradients. And so this is actually doing the correct gradient descent. So that's a complete implementation of gradient descent using the AutoGrad features of PyTorch. We can check that we are doing the correct gradient descent by implementing our own version of gradient descent. So recall that this was the gradient of the loss. So I've written a function, compute grad, that calculates this gradient based on this formula. And here is my implementation of the gradient descent. So we first initialize W as before, compute the gradient at current value W, and then perform the gradient step, or gradient descent step. So if I run this, and maybe delete these cells, you can compare the two sequences, and you can see that they match. So that's the final result that we get here and also here. The only difference, which is this interesting number here, so this has to be 0, which is approximately 0. In our implementation, it's exactly 0. But otherwise, everything else checks out. So we did a correct gradient descent using PyTorch facilities.